Today I'm going to talk about a deep learning framework to detect structural variations. As you know that long reads are certainly better to predict structural variations. You can see that short reads provide linking information between adjacent segments, but missing the whole picture here. So we need long reads to detect the whole structural variations. However, it's difficult to detect those complex structural variations. There are many challenges. First one is that for the complex events, and we don't have a very good model to build and then to looking for the mutational signature. Second thing is that all these structural variations are landed in repetitive areas, and it's very difficult to spot those mutations from those repetitive sequences. And that's why we defined a very good framework. And first one, we converted the computational problem from the text space to the image space. So you can see that we use a dot plot. So anything that is not straight line, we can see there's a mutation. We call it inversion duplications with a different color. Then we remove the background repetitive signature from the reference to reads alignment. And then the last one, using deep learning approach to really find those mutations and classify them. Okay, this is a framework we published last year in Nature Message, and there are three components: encoder and multi-object recognition pack, and then it's final graph genome representation. So this was the work that's published last year. However, once we have this one, we still have more problems coming up. So the previous version, we can only compute one genome, one site each time. But for many clinical applications, we have to know if this mutation show up in the child, but it's also in the parents. And also more tricky one is that if it's a somatic events or not. So, and currently, a lot of computation methods actually using core set merging. That's the procedure that we get final set and try to look at it. But you can see from these slides, there's a lot of false positive candidate sites. So that's why we invented the new approach that built on the previous SVision framework. We basically code two genomes on one image. So the upper level is the case, is the control genome. The lower level is the case. We can compare one sample versus many samples. We also can code different genomic contents in this image as well. By doing that, we can actually detect very little signatures. For example, if we want to find 1% allele fraction, we just need to increase it to 1K times 1K dimension. And we use the light unit framework to directly do detection of the new components, new relevant breakpoints, and new allele. Okay, the final result is actually very amazing that for the trio data, we can have a very high, very low median error rate, and we have very high twin concordance rate. And of course, the most important part is de novo mutations, that you can see that a lot of cores have a very good result from the SVision-pro, and the SNFL is also pretty good here. But we look into the manual inspection of the SNFL score. I think the majority of them still contain some errors. Okay, the most challenging part, of course, is the somatic structural variations with the extremely low allele fraction. You can see that expected, if we decrease allele fraction, all the cores have become less reliable, but still our performance, our approach is still pretty good here. So finally, I would like to thank to my colleagues actually contributed work. I'm just a presenter here. Okay, thank you.